Oh, hi there. Thank you for showing up for your learning. It is a pleasure to see you once again, all of you gathered together to hear me pontificate about various mathematical topics. Just in time for us to get started. Fantastic. So, our goals today are to be able to identify situations that involve exponential growth and exponential decay and set up and evaluate exponential expressions. We also want to be able to solve for the growth factor and solve for time. The equations for exponential growth look like this. We would have some amount of something that's growing over time or decreasing over time, and that would be equal to a multiplied by b to the t. Okay, b would be raised to the t there, and t. What is a? The initial amount. And the mathy word we use for b is the growth factor. It's the base of your exponent. That's maybe why we use the letter b for that. And a is the initial amount. Well, that's easy because it's the initial letter of the alphabet. It's the initial. And so let's carry on. If we look at this equation here, let's just analyze these equations. Okay. So 400, well, that's the initial value. Why do we call that the initial value? If I put in 0 for t, the stopwatch says 0 when you start the stopwatch, right? So time starts at 0. And then if you put in 0 for t, anything to the 0 is 1. So whatever the growth factor is, I'm going to raise it to the power 0 and get 1, and then multiply by that initial amount. Just gives me the initial amount. I just multiply by 1. So that's the initial amount, 400. The growth factor here is this number in there, 1.12. And then the percent increase, well, if I look at that, the way I would build that growth factor is I take 1 and I add r. R is the rate of change as a decimal. R is the percent change as a decimal. So this one here would be 1 plus 0.12. That means it's increasing by 12%. This is 12% as a decimal. So this is how you can set up these numbers, and I'll do some examples. You'll see me set up these numbers, and that's how you can analyze these. This one here, well, my initial amount is 243. That's 7 to the 3. And then my growth factor there is 1.6. But I can also write that as 1.60. It's not like before the decimal place. If I start adding zeros, that's pretty cool. Like you go to a job interview and they're like, we're going to pay you $40,000 a year. You're like, can you add a zero to that? And they're like, no, we can't. Or maybe they say, yeah, we can give you $40,000, point zero. And that would not change the number. Right? So if we add a zero there, I'm just showing you, is 0.6 is the same thing as 0.60. Same. And that more clearly shows that that's 60% growth. After 1 year, you'll have 60% more of that thing if you multiply by 1.6. Okay, so 60%. Let's take a look. A population of 100 frogs increases at an annual rate of 22%. So we want to identify here is our A. That's our initial amount. So we have A equals 100. Our B is equal to, well, it's growing at 22%. So let's figure out B. B is going to be 1 plus the rate of change as a decimal. R is equal to 22%. Let's write 22% as a decimal. To do that, we move the decimal place twice. Wonk, wonk, it's there now. So 0.22 is R. So B is equal to 1.22. 1 plus this. 1.22. So now we can use that to set up an equation. Once we set up an equation, we can answer this question: how many frogs will there be in 5 years? So we would say the amount of frogs is a function of time, and that's equal to A multiplied by B raised to the power T. We have our A and our B, so that's equal to 100 frogs now. It's growing by 22%, so after 1 year, there'll be 122% of the frogs. So that's 1.22 times as many frogs. But it's going to grow that much every year, so we're going to exponentiate. We're going to multiply by that growth factor every year to find out how many frogs. And we have been asked to find how many frogs after 5 years. Now we're ready to solve this. So we're going to look at A at 5. We substitute 5 in for t, and we just put it in. 100 multiplied by 1.22 raised to the power 5. That's not something I want to do in my head, or can. I cannot do that in my head. So I do it on my calculator. 1.22 raised to the power 5 equals, wow, there's going to be 2.7 times as many frogs. Then I multiply by the initial amount, 100 equals, oh, wow, there will be 270 frogs. 270. What was the decimal? 0.2. So don't worry about the 0.2 frogs. It just means there's a frog that's just about to be born at the start of the 5th year. It doesn't mean that someone did something unspeakable to the frogs. Okay. Oh, and then we finish this question by saying, therefore, there will be 270 frogs after 5 years. Cool. Cool. Okay, so that's the straightforward. Well, it's not. That's the setting up of the function and then using it to solve for different values in the future. But sometimes we might have a situation where we want to know how long will it take for a certain thing to happen. That's when we're solving for time. In these cases, our solutions are not going to be algebraic. They're going to be guess and check or graphical, or throw it into Desmos and find out. So here, we can still use the same logic, though, to solve these. A population grows at a rate of 5% per year. The population in 2003 was this. So I'm going to use this as my initial value. That equals A. A is equal to 400,000. And actually, if time equals 0, I am going to use this as my year 0. That's the year 2003. I got to start the stopwatch at some time, right? So I said at 2003, I start paying attention to this city. Its population is 400,000, and I want to know how many years after that will the population reach 1 million. Let's find out. Okay? And so this is our like A of t. This is the amount that we want to find, some population at some time, and we're solving for t. T is the question that we want to solve here. So this is how we would set it up. Oh, and our b, we need our growth factor, b. B will be equal to 1 plus r, and here is the rate, a rate of 5% per year. So r is equal to 0. Not 5, 0.05. Here is a common place where students might make mistakes, and they will use 0.5 for r. That would be 50% growth. 50% growth is dramatically different from 5% growth. Dramatically different. So we want 0.05 to get the correct b of 1 plus 0.05, and then that just equals 1.05. There's our b. Here's our a. We can set up a function now. A of t is equal to 400,000 multiplied by 1.05 raised to the power t. There is our function. And now we're going to use that to say, when will this population reach that? So what we're saying is, there is some value t that exists. There is some time in the future where this population will reach 1 million. We want to find that number time. So to do that, we're going to substitute in, on this side of the equation, 1 million people is equal to 400,000 people growing over time. Now here, we can start our guess and checking if we want, but I would recommend that you divide both sides by 400,000 to isolate as much as you can the exponent t. And then we will get 10 over 4, which reduces, your calculator will tell you that's 2.5, or 5 over 2 is equal to 1.05. I'm actually going to use 2.5 there, raised to the power t. 2.5. So really we're asking, how long will it take for this population to double and then increase by another 10%, like increase by a factor of 2.5? And let's find out how long. We could do this guess and check right here. We're going to use this to guess and check. And what I'm going to do is zoom in so I got lots of space and set up a little table for my guess and checking. I'm going to guess different values of time, and I'm going to then input that into 1.05 raised to the power t, and I have a target of 2.5 that I'm trying to hit. So let's go. I'm going to clear all this. I'm going to have 1.05, and let's guess, I don't know, what do you think? Does this look like about 50 years? Maybe 50 years it should take? Let's try 50 years. 50. 1.05 to the 50 equals, 11.4. I guessed 50, and the population actually increased by 11.4. 11.4 is much bigger than 2.5, so my guess was much too big. Well, if that was much too big, what should we try? 20? Let's try 20. Okay, you get to choose, you get to guess. So we're going to clear all that. 1.05 raised to the power 20 equals 2.6. Oh, we were really close. We're just a little big. Okay, so 20 gave us 2.6. 2.6 is still bigger than 2.5. Let's try 19. 1.05 raised to the power 19 equals 2.52. Okay, that's pretty darn close. 19, 2.52. We might, if we want to refine our guess, try something a little smaller than 19. Let's try 18.7. It's a little smaller. I actually don't know the answer. I'm just guessing. So we have 1.05 raised to the power 18.7 equals 2.49. We're even closer. We try 18.8, and it's really, really good. So let's say 18.8. 2.5. Let's say that's our answer. All right. Now, could we do this in Desmos? Absolutely. Let's take a look at Desmos. But we don't have access to Desmos on a test. Yeah, but we talked about not having a testis unit, so it doesn't matter. All right. So here we go. What we could do is put in our initial function. There were 400,000 people, and they were growing at 5% per year. That means there's 105% of them next year. And that is raised to the power x, or the power time. Clearly, we can't see this graph yet because our scale is way, way wrong. We want to see when it crosses a million. So I'm going to put in 1,100,000 as my scale. There we go. And now let's, in the x-axis, look at, we already know that 20 is going to be enough. So let's look at 30 years. Okay, here we go. All right. So here is our population graph, and we want to know, when does that population cross a million people? There it is at about 18.8, which we got by guess and check. So we're pretty happy with our guess and check. I'm pretty happy with my guess and check skills. You need to practice your guess and check skills. Okay. Another way you can be really precise here is actually graph the line y equals 1 million. There it is, and find the point of intersection. There it is, 18.78. So I could have kept guessing between 18.7 and 18.8 to find that after 18.8 years, 18.8 years, we're going to get there. Or 19 years. 19 years is close enough for this question. So if it takes 19 years for the population to reach a million people, what is our answer? Well, our answer is not 19. Our answer is 2003 plus 19. Because we decided 2003 would be year 0, and it takes 19 years after that. So, it's right now, 2022, that this would happen. Or, well, actually, just at the end of 2021, that would have happened. The population would have gone over. Okay? So that's how we solve for time, is we use guess and check, or we use graphing. And I encourage you to use both. Sometimes you can use a very quick graphing sketch to help you guess and check, to start guessing and checking in the right neighborhood. At first, we guessed 50, and that was way the wrong neighborhood. But then our next guess was right in the right area. Okay, other times you're going to have to solve for the growth factor. Let's say we have a YouTube video that has 12 views at noon, and at 6 p.m. it has 107 views. And we're told this is growing exponentially, so there's some exponential function that looks like amount of views is a function of time, where time is the number of hours, and that's going to be equal to the initial amount multiplied by the growth factor raised to the power time. But here the only thing I have is initial amount. There are initially 12 views at noon. Noon is our time 0. T equals 0. That's when we start the stopwatch. It's going to make our math the simplest. This is A. And then this is the amount of views at time 6 hours later. Okay. So we know it's grown in that amount of time to 107 views. Not quite 10 times its growth, but in 6 hours. How much is it growing per hour as a percent? That is saying, like, solve for me the growth factor. So let's take a look at how we do that. First, we're going to use this function here and put in what we know. A at 6 is equal to 107, which is the number of views it has when time is 6. And that's equal to the initial views, which is 12, multiplied by the unknown growth factor B raised to the power 6. Oh, that's unfortunate. I'm going to draw my 6 really curly so that you know it's not a B. Okay, that's a 6 there. And I'll put a dot in the middle of my 6's for this question so that you know that 6's have a dot in them. No, they're not B's. Okay, so that's 6's. All right, so now what we can do is divide away that 12 from both sides. So I get my inverse operations pen out. I'm going to divide that 12 away so that it's gone. And I have 107 over 12. So I have this equation over here. 107 over 12 is equal to what's left over here, b to the 6. Okay. Now, how do I solve this one? I want to know what b is, not how much b grows to over that amount of time. Well, let's see, 107 over 12. What is that number anyway? 107 divided by 12 equals. So it grew by almost 9 times, 8.9. Okay. And now what I can do is here get out my inverse operations pen again. I'm going to go back to blue. And I could raise both sides to the 1/6. Okay. Then I will get this number over here was 8.9. So this number in here is 8.9. 8.9 to the 1/6 is equal to b to the 6 multiplied by 1 over 6. That's just b to the 1 when I apply my power laws. That isolates b. Cool. So now if I just raise this x to the y to the bracket 1 divided by 6 end bracket equals 1.44. There's b. Happens to be my favorite number. 144. So this thing is growing to 144% of itself every hour. It's therefore growing by, yeah? Calculator thing again? Yeah, sure. Oh, you want to see the equation on top? See how up here is my raised to the power. I put this in brackets so that I'm not raising it to the power 1 and then dividing the result by 6. Yeah. I want 1 divided by 6 in brackets, and that's my power. Okay. So then, oh, yeah, no, yeah, okay. All right, so then B is equal to 1.44. Therefore, this video's views grow by 44% per hour. So that's growing pretty darn fast. How many views will this video have at noon 2 days from now? All right, how are we going to answer this question? Well, we can take this formula here. A is A multiplied by B over T. Here's my general formula. A of T is equal to A. That's a funny way to write an A. A multiplied by B raised to the power T. But we now know B. Here's B. And we now know A. Here's A. So this is A to the T equals, oh, I'll go up, is equal to, Tyler, you can raise your head again, 12 multiplied by 1.44 raised to the power t. And in 2 days, since noon, that's going to be in 48 hours. Let's see how many views this thing has in 48 hours. So we're going to go A at 48 is equal to 12 multiplied by 1.44 raised to the 48. Whew! Let's see. 1.44, going to raise that to the power 48 equals, okay, it's going to have 39 million times as many views in that amount of time. Oh, this is bigger than I thought it would be. It's going to have 40 million times the number of views. It started with 12 views, so it now has, it hasn't quite joined the billion club, but it's halfway to a billion views club. But only in 2 days. Like here. Show you that. There you go. So that's how you go ahead and solve for the growth factor, is you can take the reciprocal exponent on both sides. The reciprocal exponent is what you can do. It's a neat trick. So we're using those reciprocal exponent ideas to now solve for bases. I'm going to take a sip of coffee while people copy those ideas down, then I'll talk about some exponential decay, leaving you lots of time to get on the board with some of these skills. Or previous skills that you're not on the board yet with. That's so necessary. You know when you get 8 hours sleep and you wake up tired? You're like, that's not right.
I don't need 8 hours.
Yeah.
I don't need 8 hours sleep.
So you don't know that feeling, right?
Well, the only time I felt that feeling was on maybe a weekend. During the weekday, no.
Yeah. All right, carry on. Take a look at some decay. Can you do it? I feel like I need my blank pages out and show a couple more examples. Just pardon me one moment here. Holy, I got so many windows open. Oh, there's the thing there. Oh, cool. All right, what am I looking for? Blank pages, there they are. If I have a problem like this, x is my favorite unknown, raised to the power 5 is equal to 600. What's x? Well, what I can do is raise both sides to the power 1 over 5, and then I will solve x. Okay. Here I use my power of a power laws, so I do x to the 5 times a fifth, so that's x to the 5 over 5 is equal to 600 to the 1/5. That I can work out. 600 raised to the power bracket 1 divided by 5 end bracket equals 3.59. So 3.6. X is equal to 3.6. Let's check our answer. And even with the rounding, 3.6 raised to the power 5 is equal to 604.6. So really, really close to 600. The error came from rounding to the nearest integer. Okay, so that's how you do that. Let's take a look at a more complicated one. Let's say my x is now x raised to the power 3 over 2. Oh my goodness, that's so complicated. And it's equal to, give me a number, someone. 25. Okay. Sorry? Random question. Yeah. And how I would here solve for x. X could be like an exponential growth factor, and I've grown 1.5 times. 1.5 times. Like 18 months of growth would be 3 over 2 as my exponent. So now what I can do is raise both sides to the 2/3. Notice I just flip the exponent. I just flip it. And then raise both things to that. And then I will get x to the 6 over 6, x to the 1, is equal to 25 to the 2/3. Let's find 25 to the 2/3. 25 raised to the power bracket 2 divided by 3 and the bracket equals 8.54. So it's about 8.55. 8.55 is really close. Let's check our work by raising 8.55 to the 3 over 2, which is 1.5, and see if we get 25. 8.55 raised to the power 1.5. 1.5 is 3 halves equals 25.0005. So even after I rounded, this is still very, very accurate. So that's how you can use the reciprocal exponent as a new inverse operation to clear exponents away from unknowns and solve for growth factors. Let's take a look at exponential decay. So if you can identify exponential decay in the world, that's great. It happens quite a lot. All right. What's different about exponential growth and decay? Exponential growth looks like this. Exponential decay looks like this. Exponential decay is, oh, sorry. Exponential decay doesn't look like that. It looks like this. That's exponential decay, that one. This is not that. That's a flipped exponential growth. Okay, this one is exponential decay. It's losing more of its value early and less of its value late. But it's still bad news if it's your investment. But it's good news if it's like number of days missed to illness or something. All right, or COVID cases could be decaying if we're overcoming it. Let's say you purchased a car for $35,000 5 years ago. This year, it's only worth $19,000. How much is it going to be worth in 3 years? So we're thinking about selling our car, and we're thinking maybe in 3 years I'll get a new car. I wonder what I can get as my trade-in if today it's worth $19,000 and 5 years ago it was worth $35,000. Okay, so what we're trying to solve is what is my function, first of all. Okay, so the amount that this car is worth is a function of time, and it's exponential. It's equal to the initial amount. We'll call this year 0, 5 years ago. That means this year is year 5. Okay, so A of t is equal to the initial amount, $35,000, multiplied by the growth factor b raised to the power t. We don't know the b yet, but we do know that A at 5, like 5 years after we purchased the car, meaning today, it's worth 19,000. So let's use this to solve for B. So what we would do is have this equation here. 19,000 is equal to 35,000 multiplied by some unknown number raised to the power 5. All right? Now we divide the 35 away from both sides. And notice that 19,000 divided by 35,000 is a janky decimal, but it is a number smaller than 1, but bigger than 0. Your decay, your exponential decay, your growth factor is always going to be between 0 and 1. It'll be things like 0.7 would be 30% shrinking. 0.8 would be 20% loss. So in this case, let's see how much we're losing per year. So we would go 19 divided by 35. So we lost almost 50% of our value over 5 years. So that's 50.54. So we have 0.54 is equal to b raised to the power 5. Let's raise both sides to the 1 over 5. And we'll find out what b is by doing that. Let's see. So we're going to raise this to the power bracket 1 divided by 5 and the bracket equals, there's our growth factor, 88. So 0.88. So this means after 1 year, we have 88% of the value of the car. So every year we're losing about 12%, or here about 11.5%, because it's like 88.5. If we want to be really accurate, we'll say 88.5. Okay, so B here is equal to 0.885, meaning we're losing 11.5% every year. Okay, that makes sense? Great. Yeah. Oh, I got a thumbs up. Fantastic. Cool. So now let's use that to solve how much will the car be worth in 3 years from now. Now is year 5. 3 years from now will be year 8. So let's use our initial function. Okay. And that function looked like this. Where are we here? A of t, the amount the car is worth is a function of time, and it's equal to the initial value multiplied by 0.885 raised to the power time. We want to know A at 8, 3 years from now, because now is year 5. So that's going to be 8 years since we purchased the car. 8 years after purchasing this car, it's going to be worth, I'll move this over here, $35,000 multiplied by 0.885. Oh, that's one extra 8. 885 raised to the power 8 equals, it will be worth $13,000. $13,170.86 to be very precise. So therefore, the car will be worth $13,170 in 3 years from now. That would be wrapping up that type of question. And so you see me solve for B a few different ways. I like this method of the reciprocal exponent. If you're good at reciprocal rational exponents, you can use this trick to take exponents away from your unknowns and solve for them. Half-life, I'm not going to talk about it today. I think I've talked plenty enough. Don't you agree, Bennett? Yeah. It's like I have a great face for radio and a great voice for silent films. Oh yeah? Well, that's very kind of you to say. Tessa's like, oh my gosh, anything for a compliment, this guy. I can shut this video off now. There's nothing interesting else going to happen. All right, everyone. So thanks for showing up for your learning. And yeah, that's it for me. Any questions, hit me up by